Welcome to the lecture on composition of functions. Composition is one way to combine two or more functions by using one function as the input to another function. The notation that you'll see for composition is this little open circle, so f composed with g at x. And what that means is that you're going to use the second function, g of x, as the input into f of x. So order here is very important. You actually want to start with the second function, figure out what that is first, then take that answer and plug that into f. So for example, if I have f of x equals x squared and g of x equals x plus 2, and we want to evaluate f composed with g at 2, you're going to want to start with g, figure out what g of 2 is, and then that is going to become the input into f. So to figure out what g of 2 is, remember you're going to take 2 and you're going to substitute in that 2 into x. So 2 plus 1 will be 3. That's the answer from g of 2. Now you're going to take that and plug that into f. So for f's rule, we want to take our input, which in this case is 3, and plug that in for x. So this is going to be 3 squared. So the whole composition gives us 9. So it's kind of a two-step process. So if we do g of f of 3, remember you're going to start with the second function first. So we want to figure out what f of 3 is first, and then plug that into g. So we're going to do f of 3 first, so we go to f. F's rule is take your input and square it. Our input is 3, so 3 squared becomes 9. Now we're going to take that answer and plug that into g. G's rule is take your input and add 1 to it. So here our input is 9. 9 plus 1 will be 10. So our composition is 10. Now the next two examples here use the same two functions, but notice this time our input is just x instead of using an actual number. And sometimes these are a little bit more confusing. You just have to be a little bit more careful with your rules. So if we want f of g of x, then again we're going to start with the g function first. We're going to figure out what the rule for g of x is, and then take that entire rule, that entire expression, and substitute that into f's function. So what's the rule for g of x? G of x rule is x plus 1. Now we're going to take that whole expression and substitute that into f. And remember, the rule for f is take whatever your input is and square it. So in this problem, our input is x plus 1, and we need to square it. So our answer is a rule as well, x plus 1 quantity squared. If we reverse the direction around and do g composed with f at x, then we're going to do the rule for f first, and then take that answer and plug it into g. So the rule for f is x squared, and now we're going to take x squared and plug that into g's rule. G's rule says take whatever your input is and add 1 to it. So here our input is x squared. When I add 1 to it, I get x squared plus 1. Notice that these two answers are not the same. These are not equal to each other, because if you FOIL out x plus 1 squared, you would get a middle term of 2x, which this does not have. So what that's showing us is that f composed with g doesn't necessarily give you g composed with f. So it's not a commutative operation. It matters what order we do things in. Okay? So you just want to always be careful about doing them in the right order. Let's try another example with some different functions. This time our function f is going to be 3x plus 2, and our function g is going to be the absolute value of x. So if I want f composed with g at 3, first we're going to figure out g of 3, get that answer, and plug that into f. So the rule for g is the absolute value of your input. So the absolute value of 3 stays 3. Now take that answer and plug that into f. The rule for f says take 3 times your input, which in this problem is 3, and add 2 to it, so we get 9 plus 2, or 11. So the whole thing is 11. For the next example, now we're going to do it in the opposite order. G composed with f at 3. So here we want to do f of 3 first, then take that answer and plug it into G. So the rule for f was 3 times your input plus 2. So 3 times 3 is 9, plus 2 more makes f of 3 11. That was the same thing we had before. That now gets plugged into G, and the absolute value of 11 stays 11. So in this particular example, f composed with G at 3 was equal to G composed with f at 3. So we did get the same answer in both directions. That's not always going to happen. Okay, now let's do it for f of g of x and g of f of x. So here we're going to do the rule for g of x first, and then take that and plug it into f. So g of x has a rule of absolute value of x, and now we're going to take that and plug it into f. So the rule for f says take 3 times whatever your input is plus 2. So we want 3 times our input, and this time our input is the absolute value of x, and then we're going to add 2 on the end. So here's what our final rule for the composition looks like. If we switch the order around, now we're going to want to do f's rule first and then plug that into g. If I take the rule for f's rule was 3x plus 2, and now we're going to substitute that entire expression inside of these absolute values, because that's where the input variable should go. So we want the absolute value of the input, so the absolute value of 3x plus 2. So here's our 2 rules. Okay, let's try a couple more. Let's let f of x be x squared and g of x be the square root of x. So if I want f composed with g at -1, then we want to do g of -1 first, and then find f of that. Now when you go and you put -1 under the square root, we would end up with square root of -1. That is not a real number. So if we're only dealing with real numbers, which in this section we are, then this would be undefined, because we get a complex number, one of those imaginary number i's, because you can't have a negative underneath a square root. So if g of -1 doesn't even exist, then there's no way the composition with f is going to exist either. So this answer is just no solution. If we switch the order around and do f of -1 first, then plug that into g, f of -1 is saying take -1 and square it. Well, when you square the negative and the 1, you get +1 back. And now if we take that +1 and substitute that into g, square root of 1 does give us 1 back. So in this order it worked, in this order it did not work. Okay, let's do the more general formulas here. If we do f of g of x, we're going to do g of x's rule first and then plug that into f. G of x has a rule of square root of x, and now we want to put that into f. So f says take whatever your input is and square it. So the square root of x quantity squared, remember that a square root and a square cancel each other out, so this gives us x back again. And this is assuming, remember, that the x's that you're using are in g's function. In other words, you have to make sure that whatever x you're using is going to be in the domain of g. And since g is the square root function, which has a domain of only positive numbers, then this is only going to be true when we're in positive x's. So sometimes with these compositions you have to consider domain. Remember when we plugged in -1 into f of g, it didn't exist. There was no solution because you were trying to take the square root of a negative. So that's what I'm trying to say here. This is only going to work for f composed with g as long as the x that you're using is a positive number or 0 to begin with. Okay, let's try in the other direction. If I do g composed with f of x, then we're going to do f's rule first and then plug that into g. F's rule is x squared, and when I take x squared and stick it underneath that square root for g, is going to take the square root of its input, so the square root of x squared. Again, a square root and a square cancel out, but in this case we want x to be, x can be anything, but we want to make sure that when you take a square root of something like this, you're implying that you're taking the positive square root. So actually the square root of x squared doesn't really simplify to x, it simplifies to the absolute value of x. And here x can be any real number. So even though we kind of got x for both of these two rules, there are a few restrictions. In the case of f composed with g, you do get x back again, but you can only do this if the x you start with is a positive number or 0. If you go in the other order, g composed with f, then you can use x as any value, any real number, but what you're going to get back for an answer is only positive values because we have this absolute value of x. So here that statement that I said before is the square root of x squared doesn't really just give you x, it technically gives you the absolute value of x. So that ensures that your answer is a positive value, which is the kind of square root that we're taking here. Alright, in the next summary here, I just want to point out a comment we made earlier. In general, f composed with g at x doesn't necessarily always equal g composed with f at x, so order matters. Sometimes it does, but not always. We are also going to talk about a special relationship that's kind of like the last one we just did. If you take f and compose it with g, and you get back x for every x in the domain of g, and then you do g composed with f, and get back x for every x in the domain of f, then what we say is f and g are inverses of each other. Just like in the last example, we had f was x squared, and g was the square root of x. X squared and square root, we think of those as being inverses of each other, and indeed we did get x's when we did our composition in both orders, with restrictions on those domains. So when you talk about inverses, you talk about the fact that a function composed with its inverse should give you back x. The notation that you see for an inverse function is your normal function notation, but then you'll see this little -1 written up in that sort of exponent area. It doesn't really mean an exponent, it's just the symbol that we use to represent an inverse function. So here's the formal definition of an inverse. F composed with f inverse of x should give you back x, and the inverse function composed with f should give you back x for all x's. So think about why that would be true. If you truly do have inverse functions, then a function is going to do something to x, and its inverse should undo that, so you should get back the original x. And that's what this is saying. One of your functions does something to your input, and the inverse undoes that, so you should always get back what you started with in both directions. Okay? So for example, if I gave you these two functions, f of x equals 3x plus 2, and g of x equals x minus 2 over 3, let's prove or verify that they are really inverse functions of each other. So what we have to show is that f composed with g, the inverse, should give us back x, and g composed with f should give us back x. So whatever g does to x, f should undo that, so I get back the original input. And whatever f does to x, g undoes that and gives us back the original x. And you have to show both directions, because remember, composition is not necessarily commutative. So you want to make sure that it works in both directions. So here's what we're going to do. We're going to prove f of g of x is x. So let's find f of g of x. So we're going to take the rule for g, which is this x minus 2 over 3, and we're going to input that in to f. So here's the rule for f. F says take 3 times your input plus 2. So we want 3 times all of this input plus 2. And now let's simplify. 3 times x minus 2 over 3, these 3's cancel out because one's on the bottom and one's on the top. So all we get left over is that x minus 2 plus the 2 on the side, and these 2's cancel out, so we did get x back, and that's what we're trying to show, that when you start with x, you end with x. Okay, so that worked in one direction. Now we just have to show it in the other direction. So this time we're going to start with f and plug that into g. So the rule for f was 3x plus 2, and now we're going to input that into g. The rule for g says take whatever your input is, subtract 2 from it, and then divide all of that by 3. So here's my input, 3x plus 2. I'm supposed to subtract 2 from that, and then divide all of that by 3. When I go to simplify, these 2's cancel out, so we get 3x on top over 3. We have a 3 on the top and the bottom, so they cancel out, so we get x. And so it did work. We started with x, we ended with x, and it worked in both directions. So that is how you prove that you have two functions which are inverses of each other. So we could really say, using notation here, that if f of x is 3x plus 2, then f inverse of x is x minus 2 all over 3. Okay? Alright, that concludes our lecture on composition of functions. Good luck.